In this video, we're going to look at what is matter and how it is formed. So, in order for us to look at matter, we need to look at something that we've looked at for many years, which is periodic table. So, on a periodic table, there are various things you need to be able to read off. Elements and the atomic structure. So everything on the periodic table are elements shown on there. We call them elements because they're kind of the most basic fundamental parts. They're not always going to be in that same structure, more on that later, but these are elements because we identify them to be the most common form of what they present. Relative atomic mass. So when we talk about mass on those objects, they're not actually in grams or kilograms or anything like that. They're relative to a certain mass, which is, let's say, a proton. You can convert them to grams as long as you have Avogadro's numbers worth of atoms, but we're not going to deal with that mainly. We're really just going to look at the mass and how it affects us in terms of physics. Element number and number of subatomic particles. You should have seen those before, and then we are also looking at isotopes. So, what is an element? An element is the smallest stable structure of a type of substance. Like I said, there are different types. Again, more on that later. That's what we were talking about with isotopes. Anyway, it consists of protons, neutrons, and electrons. So protons and neutrons are in the center. If you vaguely recall, this section here is called the nucleus. And that's where the protons and neutrons are located. Each of them have a mass of 1 atomic mass unit, and it contributes to most of the mass on an element. That is why we usually disregard the mass of the electrons, which are on the outside in the electron cloud. So, to identify the elements, we use the periodic table. Now, please remember that the periodic table is arranged by the number of protons, not electrons. That is really important, especially for what we're going to do in physics. So please note the symbols of where each of the things are. Atomic mass is usually on the it's sometimes written on the bottom, sometimes it's written on the top corner, and the atomic number is written on the top left. So, to get all the bits of information that we need the proton number, which is actually the element number. The number of neutrons is the atomic mass minus the element number, or the number of protons. Because remember, most of the mass is made up of protons and neutrons. Electrons will usually be the same as protons. However, that may not always be true. But for the sake of it, for the sake of argument, let's just say they are. Nucleons is everything inside the nucleus. So that is the number of protons and neutrons. Alright, so just an example here. Find the number of protons, neutrons, nucleons, and electrons for the following. So nitrogen. By the way, always rounded to the nearest whole number for each of these. So nitrogen, if you have a look on the periodic table, it should pop up like so, where it has a mass of 14 and an atomic number of 7. So that means we have 7 protons. The number of neutrons will be your mass minus the number of protons, which is 7. Your number of nucleons, because it's the combined number of protons and neutrons, that's really just a mass. So that means we have 14 nucleons, and the electron number should be the same as the number of protons. Chlorine. Chlorine looks like this. 35 on the bottom, and then 17 on the top. So we have 17 protons. Neutrons is the mass minus the number of protons, which gives us 18. The number of nucleons is our mass, and the electrons will be 17. Tin looks like this. Yes, I know it's SN. It is a little bit annoying. We have 50 protons. 119 minus 50 gives us 69 for the number of neutrons. So the total number of nucleons is 119, and the number of electrons is 50. Alright, so now we're going to kind of differentiate between elements and isotopes. Now, like I said before, the periodic table only shows the most common types of atoms that we see. However, in nature, obviously, there's various different types. For example, if we look on the bottom, you have two types of carbon. Carbon with an atomic mass of 12, or carbon with an atomic mass of 14. You might have heard about these before. So carbon 12 is the most common one. They're the ones that we can find, say, within our bodies usually, or you can find it in any carbon-based things and life forms, even in diamond. Carbon 14, however, is radioactive, and you might have heard of carbon dating. When it says carbon dating, this is what we're referring to. It's for carbon 14. Now, because of that, we need to be able to write it in a symbolic form. So to write it in symbolic form, and yes, this is going to get a little bit annoying, the mass number goes on the top and the atomic number goes on the bottom. If you, however, remember on a periodic table, let's say I write nitrogen again, it usually has the atomic mass on the bottom and the atomic number on the top. So they are reversed, and please make sure you don't muck that up. You put the mass on the top and then the atomic number on the bottom. Alright, so oxygen. Normal oxygen has a mass of 16 and a number of 8. Iron on the periodic table is mass of 56, atomic number of 20, whoops, that should say 26. Actinium is a C. If you can't find this, it's on the bottom, on that separate section. The reason why it's on a separate section, as I will mention later, is because you can only really find it in labs. So they're lab produced. That's why their masses are kind of in brackets. They're in brackets because it shows that they're not stable. So eventually over time they do something called decaying, which I'll cover a little bit more later. Alright, uranium-235. So uranium is U, 235 for the mass, and then 92. So what that means is if you have a number written on the next to the element name, it is an isotope form of that element. If it doesn't say that, then you just presume it's the normal one. If it does say a number, then you need to write it using that number. And the number there is always the mass, not the atomic number. Remember, the atomic number is really the proton number, which determines what element you have. So the only thing you can really change is the number of neutrons. Alright, so carbon 13. Mass of 13 and atomic number of 6. So, radioactive isotopes. Now, a lot of atoms are stable, but some of the other atoms aren't. Radioactive isotopes are ones that are not stable, and so what they do is they need to give off energy to make itself stable. You can find natural ones, and you can also find artificial ones. So as I mentioned before, artificial ones can be done in labs. What you usually do, and not always, but usually, is you shoot a neutron into the center, and as you fire it into the center, the nucleus of an atom, it quite often changes. Sometimes it breaks apart. When it breaks apart, that's usually called nuclear fission, and you might know about that through various power plants. But anyway, I need to change the bottom of that. I think this is inaccurate now. Oh, sorry, not the bottom of that. Oops. Now, any number from 84 onwards is all radioactive. You might notice polonium, which is number 84. Onwards, it all has a colored square, and each colored squared shows you that it's radioactive. Now, as I said before, all the light produced ones have brackets on them. There you go, that's one. I think that's tellurium, tactium, something like that. There you go, see, another one with a number. However, let's say if I go to uranium, uranium does not have a number. That means they are only, the ones without the numbers can be found in nature, the others have to be found within a lab.